Okay. There aren't that many days where we cover content from more than one section. Today's one of those days, and I think it's because most of this content will probably be pretty familiar and mostly comfortable for you. So I'll probably go pretty quickly as we go through it, but please tell me to slow down, ask me questions if you have them. All right, here goes. We're going to start out with a probably pretty basic review idea, and that's place value. Um, when we look at a number like 4,317.265, there are place values. In here, we have the ones place, we have the tens place, we have the hundreds place, and we have the thousands place. Probably pretty comfortable, but just as a refresher. And then on the right hand side of the decimal, here we have the tenths place, the hundredths place, and finally the thousands place. Both of these keep going forever in both directions. We would have 10,000s, 100,000s, millions. On the other side, we could have 10,000ths, 100,000ths. But for the most part, most of our numbers kind of stay in this little window. One thing I do want to point out about this is when we talked about our base 10 system a while ago, I just want to emphasize how base 10 works here, because the ones place, anything raised to the 0 power is 1, so that's 10 to the 0 power. The tens place, that would be 10 raised to the first power, that's our tens place, and 10 raised to the second power would be our hundreds place, and 10 raised to the third power gives us our thousands place. So we're kind of seeing the base 10 system at work here. And we talked about this when we were converting from other bases, but just sort of a reminder that where these things come from. And it continues on the right-hand side of the decimal. You can do this a couple of different ways. You can see the tenths place and think, okay, well, that's 1 over 10. And if you remember from a algebra class somewhere along the way, that if we take a number and raise it to a negative exponent, that puts it on the bottom of a fraction bar. So here, if I have 10 to the negative first, that means 1 over 10 to the first. So that's the 10 to the negative 1 power. And then similarly, if we look at the hundredths place, that would be 1 over 100, which is 1 over 10 squared. And if I want it to be on the other side of the division bar, we just change the exponent to negative. And so the hundredths place is 10 to the negative 2. And then you can kind of see the pattern here too if you look at it. We have 10 to the third, 10 to the second, 10 to the first, 10 to the 0, 10 to the negative 1, 10 to the negative 2, and then as you would expect, the thousands place is 10 to the negative 3. And that's just looking at this from a standpoint of how our place value system is so closely tied to our base 10 number system. The names of these place value positions will be important for us as we talk about decimals and rounding. The idea that it's a base 10 system is really more of something I just wanted to show you because it reminds us of something that we studied earlier in the semester. If we are given a number written as words and we want to write it as a decimal, write the number 37 hundredths as a decimal. A key here is the fact that it says hundredths, so we know we're going to have to go to the hundredths place, which is 2 places past the decimal. And so I need 37 hundredths. Now, there's a couple of ways you can do this. Some of you are probably very comfortable just going straight, well, okay, there you go, 37 hundredths. I've written 37, it goes to the hundredths place. Perfectly fine, terrific. Others might be more comfortable saying, okay, well, it's 37 hundredths. So that's 37 over 100 if I write it as a fraction. And now I want to turn that fraction into a decimal. And you can do that with a calculator, or just by visually seeing it written this way, you can say, oh, well, 37 hundredths as a decimal would be 0.37. Like I said, a lot of review topics, especially as we get started today, but please don't hesitate to ask questions if you have them. We looked at base 10 blocks earlier in the semester where we called them cubes, longs, and flats, and this represented a 1, and this was 100, or excuse me, this was a 10, and this was 100. Now we're going to look at how base 10 blocks can be used with decimals. With decimals, this is going to be our 1. The flat is going to be our 1. And then the long is going to be 1/10. And our cube is going to be 1/100th. So we can use base 10 blocks with whole numbers, and we can also use them with decimals, because this long is just 1/10 of the 1, and then this cube back here is just 1/100th of an entire 1. So we can use base 10 blocks with whole numbers. We can also use them with decimals. Equivalent decimals. All those decimals that you see right there are equal to each other. Why? Well, if we were to write each of those as a fraction, what we would have is we have 2/10. And here we have 20/100ths. And here we have 200 thousandths. And so the reason that all three of those decimals are equal is because they all have equal value. They're equivalent fractions. All of these fractions are equivalent to each other. 2/10 has the same value as 21/100ths, which has the same value as 200 1,000ths. And so that's why all those decimals are equal. Where this takes us is to, okay, so what are those zeros doing there? And I have a question for you. And those three decimals right there, 2.08, 0.56, 20.6, in which of those is the zero not necessary? I'm going to make a poll for this and let you tell me. So in which of those is the zero not necessary? And we'll go another 15 seconds and then we'll talk about this one. Okay, strong agreement, but not unanimous. So we'll talk about this a little bit. So in which of the following is the zero not necessary, meaning it doesn't have to be there? Well, in the first one, we have 2.08. If we didn't put the zero there, it would be 2.8. That would have a very different meaning. This is 2 and 8 hundredths. This is 2 and 8 tenths. So the meaning would change. So the zero is necessary there. We change the value of the number if we get rid of the zero. In the second one, 0.56, if you wrote that as 0.56, this is 56 hundredths, this is 56 hundredths. In that case, the zero is optional. I tend to write it, especially in class like this, just to make sure that you can see where the decimal point would be. You know, if I were going to write that number, I'd probably put 0.56, because if I wrote 0.56 and the decimal point didn't show up, it could look like 56. But either one of these is perfectly appropriate for writing 56 hundredths. And then in the one at the bottom, we have 20.6. If we took the zero out there, we'd have 2.6. Well, 20.6 and 2.6 are a lot different from each other. So in that one, the zero is necessary. So the only place on here where the zero is optional, where it's not necessary, is in that one. There's one interesting case that I do want to mention. It's a number like this one, 3.60. And we've seen zeros on the back end. 3.6 would have the exact same value. And so you might think, well, why would you even bother to put this zero on there at all? And that's a great question. The reason would be, if, let's say, you were doing some kind of scientific laboratory experiment and you wanted to make sure everybody knew that the tools you were using were accurate to the nearest hundredth. In a case like that, that's a reason you might write 3.60 instead of just 3.6. They're the same. They have equal value. They are equivalent to each other. But a reason a person might write 3.60 is just to show how specific and how precise their measurement could be. This is accurate to the nearest hundredth. And so it gives an indication of precision. Might be a reason you would put 3.60 instead of 3.6. Seems like we're doing pretty good, but I want to kind of pause for a minute and give you a chance to ask any questions you might have before we start looking at fractions and decimals. Okay, terrific. Converting fractions to decimals. You've got a choice here. You can certainly use a calculator, because that fraction bar means divide. 1 divided by 2, 1 divided by 4, 1 divided by 5, 1 divided by 10. Those are all relatively easy to do. You probably know most of these already. But if you don't, you could use a calculator to convert the fraction to a decimal. There's nothing wrong with that. 1/2 we could rewrite as just 0.5, and that zero is optional there. You don't have to use it. You could just put 0.5. 1/4, we're pretty comfortable with that, especially because of money. That's 0.25. Looking at that, that would be 25 hundredths, which would reduce to 1/4. Maybe I should write that down. 25 hundredths. If we were to reduce that, we could divide top and bottom, divide the top by 25, divide the bottom by 25. Sure enough, 25 hundredths is the same as 1/4. And so 0.25 would be the decimal version of 1/4. 1/5, you might not know. A couple of ways you could go there. You could use a calculator, or you could say, well, that's 1/5. So let's see. I could multiply 5 times 2 to get 10, multiply 1 times 2 to get 2. So 1/5 would be the same as 2/10. Those are equivalent fractions. And 2/10 I can write as a decimal. And then finally 1/10. Well, 1/10, I'm just going to put 1 in the tenths place. And so we've converted all 4 of those to decimals. Relatively straightforward to do those 4. And again, you can just divide them on a calculator if you want to. How about 1/3? If I convert 1/3 to a decimal, what do I get there? Excellent, Leslie. That's perfect. What's different about 1/3 is it doesn't come out nice and tidy like those other ones. Those ones at the top came out nice and neat. If I do 1/3, I get 0.3333, and it just keeps going forever. And the way that we would say that is zero point 0.3 repeating. We do have a way to abbreviate that. We don't use it very often in our class, but it is something that's absolutely done, is a decimal like that where it repeats, we could put a bar over the top of it. And that indicates that if this is zero point 0.3 repeating, and we put a bar over the part that repeats. So we don't put a bar over the whole thing because the 0 doesn't repeat, only the 3 does. So we put a bar over the 3 to indicate that the 3 would continue. It would repeat over and over and over again. Okay. How about going the other way? Going from decimals to fractions. And we've kind of seen a little bit of this already today. So you let me know if there's anything here that gives you trouble or might be a little confusing. But 23, 0.23, that goes to the hundreds place. And so that number that's written there is 23 hundredths. So if I want to write that as a fraction, I would just write it as 23 over 100. The other one that we have here, that 4 is in the tenths place. So if I want to write that as a fraction, that's 4/10. It could be reduced. Let's see. They're both even numbers, so I could reduce and call that 2/5. You let me know if there's anything that doesn't make sense, might be a little confusing. Please don't hesitate to ask. Okay, now we get to something that might be new and might pose a little bit of a challenge, probably not too much. If I want to convert a decimal to a fraction, that was fine. It was 0.23 or 0.4, but 0.18181818. What I've got here is the decimal that I'm looking at is 0.18 repeating. And we would put the bar over both numbers because it's the 181818 that repeats. If I wanted to convert that to a fraction, well, I can't say 18 over 100 because that would disregard all of this. So there's a technique we're going to use here. It uses a little bit of algebra, but it's a pretty basic algebra concept. And I think I don't know, I get a kick out of it. I think it's pretty neat, and I hope you do too. What we're going to do is the part that repeats, that 0.181818, we're going to call that x. And if I call that x and I multiply by 100, so I'm going to multiply this by 100 because I want to move that decimal point over 2 places. I want to move it all the way to the end of whatever it is that's repeating. I want to move it over there. So I'm going to multiply by 100. And if I do that, I'll have that 100x is equal to 18.18 repeating. And all I've done is multiply by 100. What I had before was 18181818, and I just multiplied by 100. Oops. To move the decimal over 2 places. And so now I have 18.18181818. Before I go forward, is everybody all right with that? Okay, I've got this repeating decimal 0.18. I'm going to call that x. I just wanted to give it a name. And then if I multiply by 100, it's 18.18. It's a little bit abstract. Seems like you're with me, so that's terrific. Okay, so now what I'm going to do is this. I have this 100x is 18.18181818. What I'm going to do is I'm going to subtract x from this side. And because x and 0.18 repeating are the same as each other, I'm going to subtract 0.18 repeating on the right-hand side. So essentially what I've done here is I subtracted x from the left and I subtracted x from the right. That's why this is legal to do. I subtracted the same thing from both sides. And now what happens is on the left, I have 99x, And on the right, those cancel, leaving me just 18. Now I have 99x is 18, and there's only one more step to get x by itself. I'll divide by 99 on the left, divide by 99 on the right, and now I can see that this decimal that I started with, when written as a fraction, is 18 over 99. And you could try it on your calculator, and you'll see that that'll give you 0.18181818. It's a pretty nifty little trick to say, I'm going to call the repeating part x, and then I'm going to subtract it from both sides, and that's how I'll get the 18181818. This won't be a major point of emphasis in our class, but I think it's pretty cool, and I wanted to share it with you, and I want to give you a chance to try one. We can actually turn this repeating decimal into a fraction. So I want you to try one. Here goes. Convert 0.37373737 to a fraction. I'll make a poll for this and give you a chance to try it. And I agree, Nicole. I think it's really cool that we can actually make that into a fraction. We'll go another 20 seconds on this and then talk about it. Okay, unanimous. Very good. That's excellent. Very good. I think it's a really cool little trick. It's not a very hard one, but it's a very cool one. So outstanding. Very good. And it starts out really abstract. So it's not always easy to grasp, but it looks like you've done great with it, which is terrific. So I'm going to say, all right, well, I'm going to let X be, oh my goodness, 0.37 repeating. And what that means is if I multiply by 100, the reason I multiply by 100 is because it's a 2-digit repeater. If it were a 3-digit repeater, I'd need to multiply by 1,000. But since it's 2 digits, I'll go ahead and multiply by 100. And so I'll have 100x is 37.37 repeating. And all we've done really there is move the decimal point over 2 places. So now it's 37.373737. And then we're going to subtract x from both sides. Subtract x over here and subtract the thing that's equal to x over here. What that gives me is 99x's is equal to 37. And then the last thing, um, if I have, let's see, so I have 100 x's and I take away one x. And so that's how I have 99. We don't have to put a 1 in front of it, but that's just one x. So I had 100x and I took away one x. So I have 99 x's left. X is not 1. No, not at all. Um, when we write, if we write 5 times x, we would write it like that. If I write 5x, this means 5 times x. And if I were to write 2x, that means 2 times x. And so I could write 1x, which means 1 times x. But because we kind of use shorthand wherever we can, instead of 1x, I probably wouldn't write 1x if I were writing an equation. Instead, I would just say that's x. So whenever you see x, it really means 1x. We just don't write the 1 because multiplying by 1 doesn't do anything. So when I say x is 37 here, what I'm saying is 1x is equal to 37, or excuse me, 0.37 repeating. And then so down here, when I subtract x, what I'm subtracting is 1x. And so I had 100x, I subtract 1x, so now I have 99 of them left over. Okay, perfect. Last thing to do here is divide both sides by 99. Those cancel. And so 0.37 repeating as a fraction would be 37 over 99. Some more stuff with decimals. We did this with fractions. Now we'll do it with decimals. Write them from least to greatest. I'll set up a poll for this. There's a couple of different ways you can go about it, but we want to write those from least to greatest. It'll probably take me longer to type this than it will for you to come up with your answer. When we had fractions, we would find a common denominator so that we were able to compare them. And then once we were able to compare them, we could decide which was the least and which was the greatest. With decimals, there's a couple of different ways you can go about that, and we'll talk about those. One way to think of it is just, imagine that it's money and which one would be the least and which one would be the most in terms of dollars and cents. Even though we don't really go to the thousands place with money, you can kind of see it that way. We'll go another 15 seconds on this and then talk about it. Okay, not unanimous, but we do have some agreement. Let's take a look at it. I said there's more than one way to do this, and there are a couple. The way that's probably most common for most students is just kind of looking at it from left to right, whichever one has the bigger number in the tenths place is going to be the biggest decimal. So when I see, well, I have a 3 in the tenths place, I have a 0 in the tenths place, and I have a 4 in the tenths place. So this one's going to be the biggest. And then the next biggest would have the next biggest number in the tenths place, which that's 0.39. So this is going to be second, and then this is going to be the smallest. And that's perfectly reasonable. You can look at the tenths place and see which one's the biggest, and that's the one that's going to be the biggest. If they happen to be tied in the tenths place, then you just move over and look at the hundredths place. For example, if we had 0.44 and 0.41, we could say, well, they're tied in the tenths place, but this one's bigger in the hundredths place, so this would be the bigger of those two numbers. And that's a perfectly reasonable way to go. Another way to go that kind of incorporates fractions, so I kind of like that, is if we look at what this one means. That's 39 hundredths. This one in the middle, let's see, that's 46 thousandths. And then the one on the right is 4 tenths. Now, those don't have a common denominator, so we can't necessarily compare those fractions right away, but it's really easy to get a common denominator for these. If we look at the one on the left, well, what 1,000 would be the common denominator we'd want to use. Let's get them all to go to 1,000. So the one on the left, we need to multiply by 10 on the bottom, multiply by 10 on top. That would be 390 over 1,000. The one in the middle is all set. The one on the right, well, I want to get 1,000 on the bottom, so I'm going to have to multiply by 100, which means I need to multiply by 100 on top. Now they all have a common denominator, so I can see that the one in the middle is the one that's the smallest. The one on the left is the one that's in the middle, and the one on the right, that's the biggest, by looking at them as fractions with a common denominator. And then there's another way you could go. When we were given those numbers right away, we had 0.39, we had 0.046, and we had 0.4. What you can do, and it's really very similar to what we just did here, rewriting them as fractions. What you can do is just make sure they all go to the same place value position. So once you see that this one goes to the thousandths place, and that's 46 thousandths, you can write the other ones to the thousandths place. Make the one on the left go to the thousandths place by adding a 0, and we can see that that's 390 out of 1,000. And add zeros till it gets to the thousandths place, and we can see that that's 400 out of 1,000. And now we can see that this is the smallest, this one's in the middle, and this one's the biggest. So you have a whole bunch of different ways you can look at this. You can visually inspect it, looking at the tenths, then the hundredths if necessary, and keep going from there. You can rewrite them as fractions with a common denominator, or you can rewrite the decimals so that they all go out to the same place value position. And essentially what you're doing there is rewriting them as fractions, just doing it this way instead of actually writing them as fractions. Okay, let's talk a little bit about rounding. Rounding is probably something you're familiar with. We look one space to the right. If to the right is 5 or bigger, we round up. If it's 4 or lower, we round down. We're going to try a couple and see how they go. First, I want you to round 14.117 to the nearest tenth. And I'll make a poll for you. So round 14.117 to the nearest tenth. This is likely review, but just in case it's not, and I will say that rounding is something that can sometimes give students fits. Sometimes they kind of take it for granted and assume they know how to round. Sometimes just haven't done it in a really long time, so they're out of practice. Um, Sometimes I overthink it and turn it into something more challenging than it really is. And so we'll kind of figure out where we are with that and and do a little rounding practice for a little bit. We'll go another 15 seconds on this and then do it together. Okay, strong agreement, but not unanimous. So let's go back there and take a look. So the first thing, and probably the most important thing, is we're told to round this to the nearest tenth. So the first thing we need to do is find the tenths place. So in our number, the tenths place in 14.117, the tenths place where we're going to round this is right here. So place value is really important in rounding. So we're going to round this to one place past the decimal, to the tenths place. Now, how to round, we look one space to the right. If the number there is 5 or larger, we round up. If it's 4 or lower, we round down. Something that doesn't always get talked about is when you say round up or round down, what does that even mean? And it's a great question. When we're going to round 14.117 to the nearest tenth, if we were going to round down, we would get 14.1 because we're going to the tenths place. If we were going to round up, we're going to go to 14.2 because we're going to the tenths place. Essentially, what we're saying is this number that you've been given, if we were going to cut it off after the tenths place and we weren't going to have anything past there, which of these is it closer to? That's really what we're doing when we're rounding. We're saying, okay, I'm cutting you off at the tenths place. Which one's it closer to? The number that would be below it, rounded down, or the number that is above it, rounded up. That's really what we're answering. Now, the way that we answer that is we use this technique over here. If the number to the right of the position we're looking for is 5 or larger, we round up because that means it would be closer to that number. If it's 4 or lower, we round down. And when we look to the right, it's a 1. It's 4 or lower, so we're going to round this down to 14.1. Essentially, what we're saying is 14.117 is closer to 14.1 than it is to 14.2. That's what we're doing when we round. Let's try one more. And please let me know if you have questions. Rounding is something that should be simple, but sometimes students really get into internal struggles over it. Let's take a look at one more. Round 14.117 to the nearest hundredth. I'll set up a poll for this one too. We'll go another 15 seconds and then do this one. All right, very good. Unanimous on that, outstanding. So we'll go relatively quickly through this one. Then we have 14.117. We want to round it to the nearest hundredth. So the first thing we do is identify the hundreds place. That's where we're going to round. Our only two choices here are 14.11 or 14.12. We're either rounding down to 14.11 or up to 14.12. And it's a question of which one of those is this number closer to, is really what we're doing. When we look at this number, we can see, okay, here's the hundreds place. I look one space to the right. That number's 5 or bigger. So I'm going to round this up to 14.12. Great job in the poll. I feel good about that much for rounding. If you ever run into questions about rounding, don't hesitate to ask them. Okay. Most of what we've done so far is probably pretty comfortable or review or both, except for maybe the converting those repeating decimals to fractions. But there's one topic in here I do want to make sure that we're really careful with. And that's when we have non-base 10 decimals, non-base 10 numbers that we're going to rewrite as decimals, like this one. If we want to write 4 minutes and 42 seconds as a decimal, now an immediate instinctive reaction might be to say, okay, 4.42 seems reasonable enough, but let's investigate that for a minute. That would be 4 minutes and 42 100ths of a minute, right? Because that's what 4.42 minutes would be, 4 and 42 100ths of a minute. Well, just at a quick glance, without digging too deep, this 42 100ths of a minute, that's less than half of a minute. And 42 seconds, that's more than half of a minute. And what that tells me is that this can't be right. So if I want to write 4 minutes and 42 seconds as a decimal, I can't just throw it in as 4.42. Instead, I want to take into account the fact that, let's see, how many seconds would there be in a minute? Perfect. Thank you, Jessica, Stephanie. Excellent. So this isn't 4 and 42 100ths minutes. Instead, it's 4 minutes, and then 42 seconds would be 42 60ths of a minute. So I have 4 full minutes, and then instead of 42 100ths, it's 42 60ths of a minute. Let me know if that doesn't make sense, or if you're not sure where that came from. The idea is we have 4 entire minutes, and then we have 42 60ths of another minute. So in order to write 4 minutes and 42 seconds as a decimal, I think it's kind of important to do this step first, rewrite it as a mixed number, and then we'll turn that mixed number into a decimal. Well, what 42 60ths, how am I supposed to write that as a decimal? You can just divide 42 divided by 60, and that's 0.7. And so what we have here when we write 4 minutes and 42 seconds as a decimal is we wind up with, that's 4.7 minutes. Let me know if you have questions about that. It's a little bit strange, but once you see it, 4.42 can't be right because that's less than half of a minute, and this is more than half of a minute. 0.7, that seems like the right number. That's more than half. 42/60ths, not 42/100ths. It's kind of base 60. If we think about seconds and minutes and hours, that's kind of a base 60 system. And so we need 60 to be our denominator here, not 100. And then we can write it as a decimal. One more similar to this I want to look at. A person is 5 feet 10 inches tall. Write their height in feet as a decimal rounded to the nearest hundredth. I hadn't planned on doing a poll for this, but I'm going to. So I'm going to let you try this one. 5 feet 10 inches tall. I want you to write their height in feet as a decimal. And I'll make a poll for this one. It's a strange idea because we're kind of used to, decimals is base 10, but feet and inches is not. And so we have to keep that in mind when we go to try to rewrite it as a decimal. We'll go another 15 seconds on this and then talk about it. Okay, not unanimous, but definitely strong agreement there. Okay. So, keeping in mind that it's 5 feet 10 inches tall, and a key part here is that there are 12 inches in 1 foot. So, in order to have a whole foot, you'd have to have 12 inches. This person is 5 feet 10 inches tall. Now, keep in mind, we don't want to go straight to 5.10 because 5 and 10/100 of a foot, or 5 feet and 1/10 of a foot, which that's not what we've got here. We don't have 1/10 of a foot. Instead, they're 10 inches tall. They're almost 6 feet tall, not 5 feet and 1/10. That's barely over 5 feet. This person's almost 6 feet, so this way is no good. Instead, what we want to do is say, okay, well, they're 5 feet, and then they're 10 out of 12 of that next foot, 10/12ths of the next foot. So we've rewritten it as 5 and 10/12ths. And now we're going to convert that to a decimal. And 10/12ths as a fraction, that fraction bar just means divide. So we'll do 10 divided by 12, and that gives us just this 10 divided by 12 part gives us the 5.83. And now we can put those together and see that they are 5.83 feet tall. So if they're 5 feet 10 inches tall, they're 5.83 feet tall. Let me know if you have questions on that. That part finishes off section 2.3 for us, and we'll move ourselves into section 3.4 here in just a second. All right, excellent. A key topic in section 3.4 is the topic of absolute value. I'm positive you've encountered absolute value sometime before. Absolute value is where you see a number written between two vertical bars like that. That absolute value of 5 is 5. And then to go along with that, we could also say that the absolute value of -5 is 5. And when you're first learning these, and you might be a pretty young student the first time you see absolute value, and you just figure, just make it positive. And that works. I mean, you get right answers for that. We're going to be a little bit more sophisticated in our understanding of absolute value, though. Because while it's true that we make it positive, the reason that we make it positive is because absolute value is a distance. And we always measure distance as positives. If I were going to ask you, how far is it from your house to campus? You wouldn't say a negative number. You'd give a positive number, however far it is. Distance is always measured as a positive. And so the reason absolute value is always given as a positive is because it's a distance. If we look on a number line and I have 0 and I put 5 over here, well, the distance from 0 to 5, that distance is 5. And that's what we're saying. How far is it from 0 to 5? That's what this question right here is. How far is it from 0 to 5? Well, it's 5. That's how far it is. And so that's why the absolute value is 5. And then if I put -5 on that number line, and I say, how far is it from 0 to -5? Well, that distance is 5. And so that's what we're saying over here in this question. How far is it from 0 to -5? Well, it's 5. That's how far it is from 0 to -5. So a key definition for us is that absolute value is distance from 0. One of the reasons that's important for us is because of the idea of an opposite. Whenever we have numbers like 5 and -5, those are called opposites. Opposites have the same absolute value, but they're on opposite sides of 0. One of them is positive, one of them is negative. The number a and -a are opposites, and they have the same absolute value. Here, 5 and -5 would be opposites, and they have the same absolute value. So there's some terminology there that's really important for us. I don't think it's complicated. It's just really important that absolute value is distance from 0, and a and -a would be considered opposites of each other. They have the same absolute value. Where are you going with this? You might be wondering. And where I'm going is to something called the additive inverse property. We looked at quite a few properties back in chapter 3, and the additive inverse property is this, that if we add two opposites, we get 0. They have the same absolute value. They're on opposite sides. If we add two opposites, we get 0. And so that is the additive inverse property. What we also see here when we add two opposites and get 0, if I did a minus a, I would get 0. So if I take a number and I subtract it, I get 0. If I take a number and I add its opposite, I get 0. And where that leads us to is another important sort of definition terminology for us, that subtraction is the same thing as adding the opposite. And that's what we see up here above. If I start with a and I subtract a, the same thing happens if I start with a and I add the opposite of a. So subtraction is the same as adding the opposite. That's going to come in really handy for us when we have problems that involve a lot of positive and negative integers. The idea that subtraction is the same as adding the opposite. Here's what I mean. So, putting the additive inverse property to work, the idea that subtraction is the same as adding the opposite. Me personally, 14 minus negative 25, that's hard for me to manage. Even entering that in a calculator might get fuzzy for me. But because I know that subtraction is the same as adding the opposite, okay, so I'm not going to do 14 minus negative 25. Instead, I'm going to change this problem so that it's instead of subtraction, I'm not going to do subtraction. I am going to add the opposite. And a lot of times you'll see it this way, and those two cancel each other out, and that's not wrong, but more formally, what's happening here is this: subtraction is the same as adding the opposite. So I'm changing this to addition. I'm changing that to the opposite of what it was I was given. 14 minus negative 25, that's hard to do. But because I know subtraction is the same as adding the opposite, so I'm changing this to addition and I'm changing the sign of that one. That's what we've done there. Now it's 14 plus 25, and that's just 39. In general, addition's easier than subtraction, and this property allows us, this idea, this concept that subtraction is the same as adding the opposite allows us to say, okay, here, this negative 5 minus 17. I don't know about that, but subtraction is the same as adding the opposite. What we're doing is we're adding the opposite of the number I was originally given. I was originally given 17. I'm going to change that to the opposite of 17, and I'm going to add instead of subtracting. And so now I have negative 5 plus negative 17. You can think of this maybe you could do this in your head. Maybe you do it on a calculator. Maybe you do it on a number line. If I do negative 5, and then I need to go negative 17 more, that lands me over here at negative 22. And again, we're working on the idea that adding is usually easier than subtracting, and I can get rid of subtraction because subtraction is the same as adding the opposite. Finally, we have the one over there on the right, 6 minus a negative 8. Well, subtraction is the same as adding the opposite. Now that's negative 6 plus a positive 8, which you could do that a couple different ways. You could use the number line approach. Negative 6. And then from there, I need to go positive 8, which lands me at 2. You might not need to draw a number line to do that, but it lands us at 2. And again, the key concept here is that subtraction is the same as adding the opposite. A little bit of problem solving as we kind of round out towards the end of section 3.4. There's not a whole lot in 3.4, which is why we can combine it with 2.3. The Rusty Nail Saloon lost $1,300 in October. If its net worth at the end of that month was negative $800, what was the net worth at the beginning of October? And this is basically a problem where we're getting used to working with positive and negative integers. I can tell you when I was a high school teacher and I had students in my Algebra 1 class, if they were comfortable adding and subtracting, multiplying and dividing positive and negative numbers, I was home free. I could get them to learn algebra if they were good doing operations with positive and negative numbers. But it was a really difficult thing for a lot of them. And so while a question like this might seem relatively simple, it's a really important question. There's a little modeling in here. We're going to create an equation that we can solve. They lost $1,300. And the net worth at the end of the month, so I guess after they lost that money, their net worth was negative $800. What was their net worth at the beginning? So you might set your equation up differently, but they were at the beginning of the month, they lost $1,300. And then at the end of all that, they were worth a negative $800. And so there's our equation we've set up. And we'll just read through it one more time. The Rusty Nail Saloon lost $1,300. So that's this piece. If the net worth at the end of the month was negative 800, so after that, they started at something, they lost 1,300, now they're worth negative 800. What was it at the beginning? That's the thing we've called X. That's the thing we're going to try to solve for. A little bit of algebra here. I want to get that X by itself, so I want to make subtract 1,300 go away. What do I need to do to both sides? To make that 1,300 go away and get X by itself, what do I need to do to both sides? Perfect, Leslie. That's exactly right. Hopefully there's more coming that are the same thing. Yeah, we're going to add 1,300 on the left. If we add 1,300 on the left, we also have to add it on the right. Those will cancel. And so we have X. This is our net worth at the beginning of the month. The only thing left for us to do is simplify that on the right. And I have negative 800 plus 1,300. You can do that on a number line. You can do it on a calculator. What you'll end up with is 500 as the net worth at the beginning of the month. Being able to work with positive and negatives is really important. So I want to make sure that we're all comfortable with them too. Just one last note in the homework. One thing I want you to do is just look over the relationship between natural numbers, whole numbers, and integers that's